Welcome to our second Biology 12 video. Today we're going to be looking at atoms, ions, isotopes, and molecules. And if that sounds a lot like chemistry, you're absolutely correct. But to be honest, our bodies are just glorified bags of chemicals, and if we want to be good biologists, we need to have a basic understanding of chemistry. If you have Chemistry 11 and 12, this should be a very simple review. If the last chemistry you had was Science 10, you might find this a bit quick, and for further help, you could come see me at lunch, or you could go to Khan Academy, and they will discuss the same topics just in more detail. Regardless, by the end of today's video, you should be able to compare, contrast atoms, ions, and isotopes, and be able to draw Bohr models for various atoms and ions. We will then pick up the rest in class, where you should be able to compare compounds and molecules, ionic and covalent molecules, and identify the 6 major elements found in our body. So what is an atom? It is the smallest particle of an element that retains the properties of the element. It's a great textbook definition, but what does it really mean? Well, pretty much it means if you had an atom of gold and you were to try and break it into something smaller, it would no longer act like gold. An element itself is a pure substance that is made up of one type of atom. And the behavior and identity of an atom is determined by its subatomic particles. Subatomic, sub meaning below, these are things that are smaller than atoms that make up the atoms. 3 key subatomic particles are protons, neutrons, and electrons, and in particular, the number of an atom's protons, those are the positive charged particles that live in the nucleus, actually determine what type of element the atom is. For example, if you have 6 protons, you would be a carbon atom, whereas if you had 8 protons, you would be an oxygen atom. Then we have the neutrons. These are neutral, or have 0 charge. And like the protons, they do live in the nucleus, but they serve a different function where they actually act like glue to hold the atom together. Thus, they determine whether an atom is what we say stable in terms of its nucleus, or whether it's unstable, in which case it will be radioactive, and it will kick things out of its nucleus in an attempt to become more stable. Finally, we have electrons. Electrons are much, much smaller than protons and neutrons, but they play a key role in determining how atoms react. So electrons are negative. They live in the shells or orbitals that surround the nucleus, and they determine the chemical reactivity of an atom. Basically, determine what other types of atoms it will react with. Now, throughout Biology 12, we'll be referring to atoms, ions, and isotopes frequently. So it's important that we have a basic understanding of the 3 words. So atoms are always neutral. This means their number of protons, or positive charges, must equal their number of electrons, or negative charges. The number of positives and negatives equal, they cancel each other out, and you get a neutral atom. Atoms become ions when they gain or lose electrons in an effort to obtain a full valence shell. We're going to talk about the valence shell on the next page. In contrast, ions are always charged. This means the number of protons, positive charges, be careful here, cross out equals, because the number of protons do not equal the number of electrons. You either have more of one or the other, resulting in either a positive or a negative charge. If an atom loses or gives away electrons, it becomes positive because it's has less negativity, it's given it away, and it is called a cation. These are typically metals. Now remember, cation is positive because it has the big old plus sign right in the middle of the word. If an atom gains or steals electrons from another atom, it becomes negative, and it is called an anion. I remember anion is negative because it has the extra N in the word for negative. Okay, these are typically nonmetals which gain or steal electrons. Isotopes, well, iso means same. Isotopes are two atoms of the same element, but there must be a difference to them. So they have the same number of protons, but a different number of neutrons. Common example of isotopes are carbon-12 and carbon-14. They both have 6 protons, making them carbon, but carbon-12 has 6 neutrons and happens to be stable, whereas carbon-14 has 8 neutrons, not the right amount of glue, so it's unstable and radioactive. Now, this is important in biology because radioactive isotopes are commonly used in medicine. In fact, we use them for radiation therapy and for various imaging techniques, including what's called PET scans for looking at soft tissues, and diagnosing and treating various diseases such as thyroid disease, where the radioisotope iodine-131 is used both to diagnose and treat the disease. So we'll hear these more throughout the year. Now, it's important to understand how various atoms interact in chemistry and in biology. And one of the ways we can predict this is using Bohr models. Now, if you have Chem 11 and Chem 12, you're going to know there's some limitations to the Bohr model, but it is a simplistic and sufficient representation, at least for biology 12, of how the electrons are configured in an atom or ion. And we can use this to help understand and predict how a molecule will form. So before we get into the details of a Bohr model, for a specific atom, we'll just look at in general. In general, a Bohr atom will list the number of protons that are found in the nucleus. To determine the number of protons, you go to the atomic table, or the periodic table, and you look up the atomic number. I find this difficult to remember, so one of the little tricks is I use PAN. Protons equal atomic number. Then you draw the number of neutrons found in the nucleus. This is a little bit more difficult because the periodic table does not directly give us the number of neutrons. We actually have to do a little bit of math. So what the periodic table does give us is atomic mass. And atomic mass really equals your number of protons plus your number of neutrons. Now, we don't actually add in electrons because they're so tiny compared to the two, they really aren't a significant portion of the mass. So if we want to know neutrons, we got to do a simple little bit of algebra and rearrange this equation so that neutrons equals mass minus protons, or protons are also the atomic number. Then we can figure it out. Then this is all happening here in the nucleus. Surrounding the nucleus, we have where the electrons live, and these are typically called shells, orbitals, and sometimes energy levels. And these are where the electrons live. And according to a Bohr model, electrons can't just go in there any which way. They start out with, in the first level, which you start closest to the nucleus, you have a maximum of 2 electrons that fit. In the next level, you have a maximum of 8 electrons. And in the third shell, again, a maximum of 8 electrons. How do you determine electron number? Electron number depends on whether it is an atom, which if you remember from above, atoms are always neutral. So proton equals electron, or ion, which gains or loses electrons to achieve a full valence shell. Well, that's a question. What is a valence shell? This is the outermost shell containing electrons. And we will show this on the next slide or next page when we look at the model for phosphorus. At this point, we're going to stop here and we will pick up and continue in class. However, if you know you are going to be away in class or you're doing this after the fact, I'm going to pause for 30 seconds and then pick up and continue. So you can either do rest in class or you can continue along now.